All right, in Calculus 3.9, differentials. We're going to compare the value of a differential dy with an actual change in y, which is denoted as a delta y. We'll estimate propagated errors using differentials and then find the differential function using differentiation formulas. So when we had y equals x squared, the dy dx, that's the derivative, is 2x. So the differential would be dy equals, bring that 2x over, so it's 2x dx. Again, y equals 2 sine of x, so that's a coefficient. So its derivative would be dy dx equals 2 times the cosine of x. The differential, what does dy equal? Multiply this dx over, there's the differential. X times the cosine of x, this would have to have been product rule to get the derivative. So dy over dx equals, and there was from your product rule. Again, bring that dx over. Notice this all ended up in parentheses with the dx. And same thing. Okay, this is the gentleman that is, that has, basically he's the one who came up with a notation for derivatives and differentials. He was a German mathematician. So finding the differential of a function. So first we just start with finding, it's like finding the derivative, y'all, but you're just putting your dx at the end, basically. So the derivative of the sine of 3x would be the cosine of 3x, but then times the derivative of that 3x. So my differential, that means the dy would be cosine of 3x times this derivative, which is 3 dx. Normally you put that coefficient in the front, and you do keep the differential part of it at the end, the dx. For this derivative, it would be chain rule. So you would do a half, everything in there, to the negative 1/2, times the derivative of what's inside, which will be 2x dx. This 2 and this 1/2 do simplify. So I get x on top, the square root of that on the bottom, and then the dx to the side. Now we're supposed to compare a delta y with a dy. So first says let y equals x squared. Find dy when x equals 1 and dx is 0.01. So here's y equals x squared. Do the differential. So it's 2x dx. So plug in the x is 1, plug in the dx is 0.01, and my dy would equal 200ths. Now it says compare this value with delta y for x equals 1 and delta x is 100th. Y'all, all that means is, and this is how they're going to write it, I prefer to use a table of points. I hope I did that in my notes. It looks like I did not. So let me write one real quick. So I would prefer you go ahead and make an XY table. The first x value is going to be 1 because they told you that. They told you your delta x had to be 0.1, so that means you're going to go up by that. So here's what you would start with your table for. So again, it said start with it said start with x is 1. So my table starts with x is 1. My delta x is a positive 100th, so that means my delta x should go up by 100th. Now take and plug both of these values into this original function here of x squared. So when I plug those into x squared, 1 squared is 1. 1.01 squared, okay, we would need to take that value. So let me grab my calculator. So 1.01 squared is going to be 1.0201. So here's my XY table. So when my delta x was 100th, my delta y, how much did this change by? It changed by 0.021. It's what it went up by. Notice there's the answer, 0.021. So again, if you want to use it with this notation, absolutely feel free to do so. Basically, we were looking for is that f of 1. If you go up on your x's by 100, then what's the difference in those y values? Okay, and it's the new value minus the old value. If you did it with a table, okay, when x went up by 100, what did y do? Y went up by this value right here. All right, so there it is from the differentials, and there was the change in y. So the measured radius of a ball bearing is 7/100ths of an inch. If the measurement is corrected within 1/100th of an inch, I said 7/100ths, that's 7/10ths of an inch. The measurement is corrected within 1/100th of an inch. Estimate the propagated error and the relative error in the volume V of the ball bearing. So y'all, we know the volume of a ball, the volume of a sphere is 4/3 pi r cubed. So if I do the differential, that would be dV equals this derivative 4 pi r squared dr. Now we know that the radius is 7/10ths. We know it's correct, so that means the dr is within 1/100th of an inch. So 4 pi 7/10 squared times the change in the radius, which is within 1/100th. We multiply all this out, and this is how far off this volume could be. So, okay, so it's that far off. But see, if the original volume was 1, we might consider that kind of off by a lot. If the original volume is 5/10, then that's definitely off by quite a bit. If the original volume is 1,000, then this really is not much to be off by. 1,000 mean 1,000 cubic inches. See, so right now, guys, this is just the propagated error. That's just what is the error. How off is it? The relative error means relative to what the actual volume of the ball is. So my relative error, I would need to figure out what the volume is at 7/10 of an inch. So I plug in the 7/10 in here. You could do the simplifying and reducing. Some people go ahead and just find what this volume is at this point, and then they take that answer and they divide by this new volume. Now, if you do the reducing, the pi's cancel, the 4's cancel, this 3 comes up, r squareds cancel, and you get an r on the bottom. So it's 3dr over r. So this was off by that much. There was the r. So therefore, this is off by 4.29%. See, this didn't sound like much. See, the volume to be off by basically 6/100ths of a cubic inch, that sounds like it's very little amount. But when we talk about relative error, see, it's relative. It's actually off by 4.29% of the actual volume of the ball. So depending on how accurate we need to be, what are we dealing with here? Are we dealing with like brakes on a car and we need them not to give out? Are we dealing with the comfort of the band on an underwear? The comfort of the band on the underwear, and somebody's not going to die from that. So maybe my machine could be off, and maybe it can even be higher than that. If we're talking about brakes on a vehicle, I don't need those going out. So I might want to have a smaller relative error if we're talking about brakes on a vehicle. All right, it says the side of a square floor tile is measured to be 4 inches with a possible error of 1/32 of an inch. Use differentials to approximate the possible propagated error in computing the area of the square. So the area of a square is x squared. The differentials, dA is 2x dx. The side of the square is 4. It's off by 1/32 of an inch. We multiply that, and that's how off it can be. That's the possible propagated error in computing the area of the square. It could be off by 1/4 of a square inch. The measurement of the edge of a cube is measured to be 8 inches with a possible error of 4/100ths of an inch. Use differentials to approximate the possible error and the relative error in computing the surface. So the measurement 8, so the area, this is talking about all about area in here, guys. Okay, so it's talking about the possible error and the relative error in computing the surface area, this should have said. So the area is 6x squared. So the differentials, plug in 8 for the edge, 4/100ths could be off by. You multiply that, and this is how off the area could be. So relative to what? See, it's off by 3 and 84/100ths of a square inch, but that means relative to what? So again, you would divide that by the original area of the square by plugging in the 8 inches here. So the relative error would be this number, the differential, divided by the actual area, 6 divided by the 8 squared. That's the 6 times 64. And so it's actually only off by 1%. So it's really pretty small. This is pretty accurate then. That ends our chapter 3. I hope you guys were understanding this last section and kind of enjoy 3.9. It kind of is a nice little break from some of the harder problems in the chapter. Y'all have a great day, and we will see you tomorrow.